So next example is deuteron, which is, I think, hydrogen with an extra neutron or a neutron. It enters a uniform electric field through a gap in the negative plate. So in the negative plate there is a gap for some reason, and this deuteron is entering via said gap. We want to know what the electric field strength is if the potential difference is 2.5 volts. The distance between the two plates is 20 centimetres, and we can just use our magnitude of electric field equation, which is E equals the potential difference divided by the distance between the two plates. So we'll have 2.5 divided by 0.2, and that will give us 12.5 volts per metre. So now we're told that deuteron has a mass of 3.348 by 10 to the negative 27 kilos, and its charge is positive 1.6 by 10 to the negative 19. We need to calculate its acceleration. That charge makes sense because if it's a proton plus a neutron, the neutron's not going to have any charge, so it should still have the same charge as a proton. Anyway, calculating its acceleration, we can just use, same as before, the acceleration equation. Acceleration is equal to electric field strength, or magnitude of the electric field, by the charge of the particle divided by the mass of the particle. We know all three of those things, so it's just a matter of entering them in. So electric field, or the magnitude of the electric field, is 12.5 volts per metre. The charge is 1.6 by 10 to the negative 19 coulombs, and the mass of the particle is 3.348 by 10 to the negative 27, and therefore our acceleration will be 6.0 by 10 to the 8 meters per second. The next question is asking, or is letting us know, that deuteron enters the field travelling vertically at 1.1 by 10 to the 4 meters per second. What is the time it takes to return to the negative plate? So if we go back to the terrific diagram I drew, so the deuteron particle, it's got a velocity upwards, so it's going to enter the field like this, but because it's positively charged, it's going to be attracted to the negative plate, so its acceleration is going to be in that direction towards the negative plate. So eventually its velocity is, because of the acceleration, or the negative acceleration, so the acceleration in the opposite direction to the velocity, its velocity is going to dwindle all the way down to 0. It will stop momentarily before moving back towards the negative plate. So we're going to have to work out first the time it takes to get from its initial position to here, and then we're going to have to work out the time it takes to get back down, which will just be the original time doubled. So they're the two steps for this question. So to work out the time taken to get to that halfway, or not necessarily halfway, but to get to that momentary stop in motion, we can use V of the vertical velocity final is equal to V vertical velocity initial plus acceleration by time. The vertical velocity final is going to be that point where it stops momentarily, so it's going to have no velocity at that point. So we can get rid of that term there. So we can then just end up rearranging. So to find the time, we'll be dividing the negative vertical velocity, the negative initial vertical velocity by the acceleration. And if we remember, the acceleration was 6 by 10 to the 8 meters per second, but that acceleration is acting in the opposite direction of the motion. So here we've just worked out the magnitude of the acceleration, but because it's entering with a velocity this way, but it wants to, or the force is acting in the opposite direction, this will be negative. So we'll have negative and then the initial velocity, which is 1.1 by 10 to the 4, and then our acceleration will be negative 6.0 by 10 to the 8. That will end up being 1.83 by 10 to the negative 5 seconds. And then to find the total time, it's just 2 by this time. So we'll end up with 3.67 by 10 to the negative 5 seconds. And that's our total time it takes to return back to the negative plate. Next, we want to find the vertical velocity of deuteron just as it reaches the negative plate. And we can do this using the vertical velocity final, which will be what we're looking for, and that's equal to the vertical velocity initial plus the acceleration plus time. Now, in this situation, we're going to think about the deuteron particle as it's already reached that point in the between the two charged plates where it's momentarily stopping and then turning back to come back towards the negative plate. So in this situation, the initial velocity is going to be 0 because of that momentary pause before it switches its direction of motion and comes back towards the plate, the negative plate. So we'll be able to get rid of that term. The velocity, or the final velocity, will be equal to acceleration by time. The acceleration is 6.0 by 10 to the 8, and the time, we only need to use the half of the total time because we're only thinking about from the point where it stopped back to the negative plate. So this will be 1.83 by 10 to the negative 5. And then this in your calculator will be 1.1 by 10 to the 4 meters per second. This is kind of similar to projectile motion where the velocity going up, if it's at the same displacement from the ground, then the velocity will be the same coming back down. So if we recall, this was our initial vertical velocity. So they're the same. The last question is asking, what distance does deuteron cover upon momentarily stopping before returning back towards the negative plate? So how far does it go before it stops and turns around? We can figure this out by using this equation of motion. The displacement will rearrange to vertical velocity final squared minus vertical velocity initial squared over 2 times the acceleration. In this case, the vertical velocity final will be 0 because we're thinking about from where it starts to when it reaches all the way to that point. So the final velocity in this situation is going to be 0. So whichever one is a 0 velocity, whichever out of the vertical initial or vertical final velocity is 0, depends on what frame of reference you're thinking about it in. So this term here will cancel, and we'll be left with displacement is equal to negative and then 1.1 by 10 to the 4 squared over 2 by negative 6 by 10 to the 8. This is because acceleration is acting in the opposite direction to the motion, so it's negative. And then if you pop it into your calculator, you'll end up with 0.1 meters. So that's how far it's travelled in this 20 centimetres between the 2 points. It's travelled 0.1 meters, so 10 centimetres, halfway.